So now, having introduced feedback, let's have a look to see what its effect is on the whole circuit. The question that we want to answer is, what is the gain of the whole circuit, X out divided by X in, after we add the feedback part of the circuit beta? Let's call the signal actually entering the internal amplifier of the circuit X in brackets int. This then is the input signal minus the feedback signal. X in int equals X in minus XF. But XF is beta times X out. We'll substitute this into the first equation instead of XF. But the output signal X out is the internal signal amplified by A. Let's substitute this into the last equation. Now cross multiply by A, take the X out terms onto one side and factorize. Divide through by A and X out and then invert. So this expression now gives the amplification of the whole circuit, the forward amplifier A and the feedback network beta. Now let me show you something very interesting. First, let's divide the top and bottom by A and cancel. Now imagine that A is very large. In this case, 1 over A would be vanishingly small, and so the whole expression would tend to 1 over beta. You might like to pause the video here and ask yourself, what does this mean in terms of practical circuitry? Did you get it? It means that providing that the amplification of the main amplifier A is large enough, and remember with op-amps it's a very large amplification, then the gain of the circuit with the added feedback only depends on the feedback part beta alone and not on the amplifier. You'll see in the videos coming up that in real op-amp circuits, beta is often simply passive components like resistors, and so we can configure the entire circuit to have any gain that we want just by using a couple of external resistors which form the feedback loop.